We now want to explore the concept of the stability of an equilibrium position if we know some potential energy function that an object is subjected to. Okay? So the idea of stability is that if you know what the potential energy function is going to be, the stable points within that function are going to be the local minima of that function. Okay? Now, in terms of calculus, we know that a function arbitrarily can have local maxima or local minima, but it's the local minima we're after. And we can see it from this particular plot of just a generic potential energy function, and I'm just going to restrict my comments to the region between these two initial and final positions. So we're really only interested in this window right here. And as you can see, there are three local maxima or minima, and we have two minima, one right here and one right here, and then we have at the top of the hill this local maxima. And what we are indicating here is that if I'm at the bottom of a bowl shape region in my potential energy function, then that is a region of stable equilibrium. If I'm at the top of the hill, as in right here, then I'm going to have an unstable equilibrium position. And you can convince yourself that that's the case. Let's say that I just put a small object in this potential energy function, and I just place it right at that particular minimum. It's not going to continue to move. Furthermore, if I displace it slightly to either side, let's say that I take it and I pull it up over this way just a little bit and let it go, it's going to be released and it's going to try and fall toward the equilibrium position, but it's going to have a little too much kinetic energy to stop, so it's going to overshoot and then come back up this way, but then it's going to run out of kinetic energy and it'll fall back down. It'll just keep oscillating, kind of like a pendulum or a spring, about that particular point. The unstable equilibrium situation, however, if I place a small mass at the top of the hill and I give it a gentle touch one way or the other, it is going to either fall this way or fall that way. And so in that case, the object is going to move away from the equilibrium position and not toward that particular equilibrium position. So an unstable equilibrium means that if I have an object right here and I displace it slightly, it's going to move off one direction or the other and not come back, as opposed to the situations in the bowls here where the object is always going to try to come back to the equilibrium solution, and if the system is frictionless or if the system is ideal, it'll just oscillate about that equilibrium position with amplitude equal to the small displacement that I gave it. That statement will make more sense as we study oscillating systems shortly. But what I want to do now is look at how do I evaluate the stability of a region. Okay, how do I evaluate the stability of a region? So we know that local maxima and minima can be found from calculus through the derivative of a function, and what I do is I set that function equal to 0 and solve for x, and we can see why from the graph. At these positions here, the derivatives are going to be flat lines. Where you have a turning point in a graph is going to have a derivative of 0 or a slope of 0 at that point. And so at those points, we set the equation equal to 0, since that's what the slope should be, and then solve for x and find what those positions ought to be. Those give us the maxima or minima, but they don't tell us whether they are maxima or minima. What we need to do then is apply the second derivative test. And if I apply the second derivative test, if I find the second derivative of my function and plug in the values of x that I got from my first derivative, then, and I plug that into my second derivative result, if that result is greater than 0, then my region is a stable equilibrium. If it's less than 0, then my position is an unstable equilibrium. So let's just do a quick example here and see how to do this explicitly. So imagine that I have some potential energy function x squared minus x. All right, and I want to know where the equilibrium points are and if they are stable or if they're unstable. All right, so what we do first, let's take the derivative, and this is going to be 2ax well, we can keep the a constant out here, and this will be 2x minus 1, right? And we'll set that equal to 0. And so now we're going to have, well, I can divide both sides by a, and so this gives me 2x minus 1 equals 0, 2x equals 1, and x equals 1/2. So this shows me that I'm going to get one point of equilibrium, okay? 1 point of equilibrium, but I don't know if it's stable or if it's unstable. So now we apply the second derivative test. So now, what I want to do is I'm going to take the second derivative of my function, and this is going to give me a times 2. Okay, so this gives me 2a. Now in this case, because x disappeared from our second derivative, then that means that we can't actually plug this value into this function, but what can we say about it based on this? Well, if we assume that a is a positive constant, and I should have mentioned that explicitly at the beginning, if we assume a is a positive constant, then this quantity is going to be positive, and therefore it's going to be stable. So this is the region at the bottom of a bowl. And in fact, if you actually plot this function for some arbitrary a, x squared minus x, you'll find that this is indeed a stable equilibrium. All right, we'll see you next time.